9. Depict electron configurations for each of the following. Wow. This is going to be a long question. Good. Let's see. Hopefully you can sit with me type through this as I solve this question. So, depict electron configuration for each of the following. I'm just going to write everything down here. So we have A is chromium, chromium 2 plus, and chromium 3 plus. B is copper, copper plus, and copper 2 plus. C is vanadium, something like that. Vanadium 2 plus, and vanadium? No. 3 plus. So those are the ones that they want us to do. So if you're worried about not getting enough electron configuration practice, well, there you go, because this is going to be a good amount of practice here so we can get extremely familiar with this. So with that being said, okay, let's see what we have here. Let's start with chromium. Okay, for this, as a disclaimer, I am going to use a shorthand for electron configuration. Now, if you don't remember me saying it, is that you want to start first with the noble gas from the previous row, and then you just go on as normal. Okay, because you know, to get to helium, it's 1s2, that's helium, and then neon is 1s2, 2s2, 2p6, and then argon is 1s2, 2s2, 2p6, 3s2, 3p6. Okay, and that's, I just wanted to set that up there because just in case we were wondering. So let me actually put this here. That's helium, this is neon, and this is argon. Oops, AR, not silver. So with that being said, this argon, and now we want to do chromium first. Okay, chromium is right there. So what is V? Oh, vanadium. Oh, it's close. Probably butchering that name, but exactly. So chromium is going to be 4s2, because where we started, the fourth row. But because you got into actually now the D subshell, okay, this we want to actually subtract. We want to subtract 1 from the row, I mean from the number, so you actually have 3d4. Okay, but we're not done here actually. So for the D shell, it's actually better if you look at the orbital notation for this, because considering that it's 3, you actually want to put it first, but D orbitals actually need to have 10 filled, and then we have the S orbital here. So we have 3d, 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 4s. Okay, and we have, as I said, 4. And then we have this. As you can see, that's kind of greedy of the S row, especially when you're dealing with D orbitals. The change from the D to the P or the S shells, there is quite a bit of energy difference. So for an actual more stable element, I'd actually prefer to have its D subshell at least filled with 1 electron than just conveniently doing, like, you know, having the 4s2, because that is exactly, it is quite greedy for this S. So what happens here is that this one electron would actually move and would actually be placed over here. This would actually stabilize, at least for the orbital notation. This would actually be a more stable chromium. So if we actually rewrote that, it would actually be, again, starting with AR. Okay, will be 3d5 4s1. This right here is chromium. Okay, so now let's think about this what happens if we lose 2 electrons? It would most likely want to lose it from its most outer shell, and considering that the most outer shell is this, I'm gonna actually have to use maybe a pencil to kind of cross it out. This will be the first one it loses, and then it'll lose one of these. So Chromium 2 plus in that case, okay, would be AR, still starting with silver, but 3D 1, 2, 3, 4. And then if it was Chromium 3 plus, same concept, but this side has now lost this one as well. So it would be AR 3D3. Now I do want to just make sure that at least we're solving this correctly, so let me just double check here. Yep, 3D4, and they do actually mention that you know, it's gonna be 4s1 3d5 because of the whole orbital notation as I showed. That's good. And yep, 3d3, perfect. So with that, we can kind of box chromium, knowing that yes, we solved that correctly. So now let's move on to the next one they talk about, copper. So copper is also on the 4th row, so you can actually start with silver again. Okay, copper, copper plus, and copper 2 plus is what they mentioned. Okay, so we have the same thing here. So first, let's start our mock work up here. It's going to be that argon again, 4s2. Okay, and then we have 1, 2, 3, 4, 5, 6, 7, 8, 9. 3D9. Now this one's a little bit trickier, but it actually follows a similar situation as the one shown earlier. It's still in the 3rd subshell, so it actually would prefer to be the one that's filled, because if we drew out the copper one, okay, using I guess the one we have here, okay, we have the 4s2. Okay, whoops, facing the opposite way, but 3D 9. So we have, it's literally almost there, just missing this one right here. Okay, so what it would actually do is that it would take this one and place it in this row, only because exactly we're still in the 3rd subshell, so exactly the energy difference is significant enough to where that would be more stable. So for this, we actually have AR, okay, 3D10 4s1. And now you actually see why it would be easier for copper to just lose 1 electron. Well, I mean, it can, because it's a transition metal, it can actually kind of choose which electrons to lose. But you see here, it'll be 3d10 by itself, because all I just did was get rid of the 4s1. Okay, and now for 2 plus, this one is a little bit trickier, but I just want to say that if you just lose another one, it'd prefer to keep everything still in its 3rd subshell, so just be 3d9. Now let's see how we did there for that one. Okay, yep, 3d10 4s1, so we're on the right track. 3d10, okay. The moment of truth, 3d9. Whew, good. So I guess the lesson here as we're going through this is that you wanted to get rid of the higher number of electrons first. So like in the higher shell, orbital shell, and that was a 4, hence why it was having an easier time getting rid of the 4s1 first. Okay, so now with that being said, let's move on to vanadium. Okay, so hopefully this time we won't have to self-doubt ourselves. Let's see what vanadium is dealing with. Okay, so vanadium is, let's erase these and see exactly Oops. What we're dealing with here. So the scratch work here. Vanadium starts with AR like the rest of them. Okay. And it'll be 4s2 3d3. Now this one is a little bit tricky because it's not like 3d4 where it's super close, but is it close enough to where it wants to because exactly the difference still is that I mean, some things will still have the same orbital notation. The difference being exactly how many protons they have. So there's still, remember, there's still different elements. Okay, so I'm gonna go on a limb here and say that it would still prefer everything in its D subshell. So for V, V2 plus and V3 plus, I believe that's the ones that they wanted. Let me see. Yep, I'm gonna go on a limb and say that we have still the silver, but it wants to stay with the same electron. Let me see here. So if we have 3 here and 4s2, as I mentioned, that's extremely greedy. So both of these actually would have to leave. So just kind of balances out the third subshell, kicking those two out. Give me a second. This is so far my theory, based on everything we've done. So hopefully it does follow that trend. So it'll just be 3d5. And as I mentioned, because these elements do have different protons and such, you don't have to worry about them looking the same way, because of the fact that, you know, it's not the same elements, different protons, different neutrons. So the electron configuration, it's the part that may seem similar. So 2 plus, it would just be 3d3. And 3 plus should be 3d2. Let's see if that's correct, or if it just broke that rule. Oh, it did break the rule. Interesting. I guess when it's not close to filling that shell, it doesn't bother moving. Interesting. So 3D. So I guess the rule is based on, I guess, as you see here, when there's only one difference, because it still doesn't want to completely lose its fourth orbital just yet. So just like if it's cost effective, because I think if I remember correctly, it wants to be able to fill each subshell group at least one electron. So if I have to get rid of both from the fourth one, then it's already expending a little bit too much energy to try to balance itself out. So it would make sense to why it would want both to just stay in the 4s. So it would be 3d3 4s2. But it also explains why I can get rid of the now this is the tricky part. It explains why I can get rid of the fourth subshell so easily. Now for this one, actually, I'm thinking that this one, instead of it being just getting rid of the 2 shells here and that, it might actually just end up being 4s2. It might have just gotten rid of its third orbital. Not sure. This may be incorrect. I'm gonna start and we'll see. Yep, 4s2, 3d3, okay, 3d2. I see. So it kind of just keeps shedding from the outside in then. Okay, that makes sense. So this will be all for vanadium. Definitely the trickiest one of the bunch, because I think this is the part we have to really understand, is that as you see here, if there's going to be too much energy used trying to fill up both shells instead of just one, like it wasn't just missing one, it was missing both, kind of like what we did with chromium, it'd rather just stay in a spot. So that's what we have here. But when we do start getting the ions, it'll just shed from the most outer shell. So the 4s2 will be the first to go, and then it'll just lose another one from the third subshell. Okay, so with that, this is correct. Okay, definitely much heftier question. Glad we were able to get our